Okay, welcome guys. So we have this question here that says we need to prove by induction that this expression here is true. So first things first, we go to step number 1 here, where we say we need to show that the statement is true for n equal to 1 here. So to show that the statement is true for n equals to 1, we're going to get this expression here, we equate it to the right hand side this set here. So where there's n here, we're going to substitute with a 1 there. So we have 1 plus 1 over n equal to n plus 1 like this here. So now when n is equals to 1 like we said here, so we're going to have 1 plus 1 over 1 is equal to 1 plus 1 this side. So this side we're going to have 1 plus 1 to give us a 2, which is equals to 2 this side here. So meaning that here we just say therefore true for n equal to 1 like this here. So then we go to step number 2. So step number 2 is the inductive hypothesis. So here we make the inductive hypothesis. So on the inductive hypothesis here, we make an assumption where we assume that, okay, sorry, let me just erase that. Okay, so here we make an assumption where we assume that the statement is true for n equal to k like this here. So meaning that we're going to write the expression the way it is, then what is n there, we're going to put k here. So meaning that here we have 1 plus 1 over 1, and also we have 1 plus 1 over 2 like this. We'll have 1 plus 1 over 3 like this, and dot 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 1 plus 1 over k here is equals to k plus 1 like this. So here this is the only thing that we get to do on the inductive hypothesis. So then we need to make another claim now that it's also true for n equals to k plus 1, so which is a statement that we're going to use to back up or rather to back the inductive hypothesis here. So we need to show that it's also true for n equal to k plus 1. Let me just scroll down a bit. So you have 1 plus 1 over 1, 1 plus 1 over 2, 1 plus 1 over 3 here, and we have 1 plus 1 over k. And also we put a new term now where we're going to say k plus 1, so meaning that here we're going to have 1 plus 1 over k plus 1 being equal to k plus 1 like this here. Okay, so now here if you look at this term here all the way up to this term here is what we have here on the inductive hypothesis there. So meaning that we're just going to get the right hand side of the inductive hypothesis and we plug it there. So meaning that we're going to have our k plus 1 like this, open brackets, we have 1 plus k plus 1 like that, we close, being equal to, so if we add 1 and 1 here we're going to get a 2 there, so we have k plus 2 like this here. So then here we're going to multiply, or we distribute this into the brackets here. So k plus 1 multiplied by 1 here, we're simply going to have k plus 1 plus k plus 1 multiplied by 1 this side, we're going to have k plus 1 divided by k plus 1. So here being equal to k plus 2 like this here. So then here k plus 1 divided by k plus 1, we're simply going to get a 1. So here our k plus 1 plus 1 equal to k plus 2 like this here. So 1 plus 1 here will give us a 2 there. So we have k plus 2 is equal to k plus 2 like this here. So we have that the left hand side here is equal to the right hand side. So now if this is the case here, then we just say this is true for n equal to k plus 1. So if it's true for n equal to k plus 1, so we say this holds under mathematical induction. Okay, let's look at the next question then. So the next question, we have to prove that this statement is also true by mathematical induction here. So we do the same steps that we did in the previous question there. So here we say we need to show that it's true for n equal to 1. So we get this expression here, we equate it to what we have this side. So this side we have 1 minus 1 over n plus 1 equal to 1 over n plus 1 like this here. So now when n is equals to 1 here, we're going to have 1 minus 1 over 2 being equal to 1 over 2 this side here. So meaning that here we're simply going to have half is equal to half this side. So therefore true for n equal to 1. So we go to the next step, which is the inductive hypothesis. So in the inductive hypothesis, we make an assumption. So now, on the inductive hypothesis here, we make an assumption, or we assume that it's true for n equal to k. So meaning that what we write the expression the way it is, then what is n there, we're going to put to substitute with k there, or replace with k. So we have 1 over term, then we have the next term 1 minus 1 over 3, then we have 1 minus 1 over 4, then we have 1 minus 1 over k plus 1 here being equal to 1 divided by k plus 1 like this here. Okay, so then we need now to show that it's also true for n equals to k plus 1. So here we need to show that it's also true for n equals to k plus 1. So we get this expression the way it is here. So we have 1 minus 1 over 2, or 1 minus 1 over 3, 1 minus 1 over 4, and we have 1 minus 1 over k plus 1, then 1 minus 1 over k plus 1 being equal to 1 over k plus 1 like this here. So we're going to simplify this expression here so that it's equal to what we have on the right hand side this side. So if you look at this here, all the way up to this step, it's this step that we have. So I'm just going to substitute here with what we have this side. So we have 1 over k plus 1 minus, open brackets, 1 minus 1 over k plus 1 plus 1 like this being equal to 1 over k plus 2 like this here. Okay, so we proceed. So now here, this is simply 1 over k plus 1, open brackets, 1 minus 1 over k plus 2, close, being equal to 1 over k plus 2 like this here. Okay, So now what we're going to do here is we're going to start simplifying what we have on the right hand side there, or on the left hand side, so that it's equal to what we have on the right hand side this side. So if you multiply this here by what we have inside the brackets there, you're simply going to have 1 over k plus 1 minus 1 over k plus 1, and also k plus 2 like this here, being equal to 1 over k plus 2. So this side, our common denominator, k plus 1, k plus 2, like this. Then this here into this, we're simply just going to have k plus 2 minus this into the common denominator that we have, we're just going to have 1 multiplied by 1, which are that term there, being equal to 1 over k plus 2 like this here. So we go ahead and simplify this expression further. So 2 minus 1, we're simply going to have 1 there. So I have k plus 1 divided by k plus 1, k plus 2 like this, being equal to 1 over k plus 2 like this here. So you notice that this term that we have on top, this and that term are going to cancel, hence we're simply going to have 1 over k plus 2 being equal to 1 over k plus 2 like this here. So you notice that here we have our left hand side being equal to the right hand side this side. So now if this is the case here, we can just say therefore true for n equal to k plus 1. So if it is true for n equals to k plus 1, then we can just put a small statement here, a concluding statement there, where we say then this holds, and mathematical induction.